Welcome to Chapter 5, Part 5. We're going to use the heats of formation in order to calculate the heat of reaction. So we've talked about two other mechanisms in Chapter 5, Part 3 and Chapter 5, Part 4 on how to calculate delta H of reaction. So in this case, we want to use the heats of formation. So the heat of formation is a table. So this information comes from a table. And so we can use these tables and we want to calculate how much energy it takes to make something from its parts. So delta H naught F, or delta HF, is the energy to form 1 mole of any given substance. Note, in a specific state. And so this tells you if you're making a gas, a liquid, or a solid. So the standard enthalpy of formation, which is delta H naught F, is the standard enthalpy at 1 atmosphere and 298 Kelvin. So this is the change in enthalpy for the reaction that forms 1 mole of the compound from its elements. So if we have carbon solid plus half a mole of oxygen of O2 gas to create carbon monoxide gas, so in this case, we can calculate or read from a table that delta H naught F, in this case, is negative 110.5 kilojoules. And so in this case, we can figure this out. And so one of the things that we can do is we're going to next look at one of these delta heats of formation table. So this is a standard enthalpy table. This is the one out of your book. On an exam, this would be provided. So this isn't necessarily something that you need to memorize, and I definitely don't advocate for you to do that. But what we can see is that we can read stuff off of the table. So let's just look at a couple of these examples. So if we think about methane gas, the delta H naught F in that case is negative 74.8 kilojoules per mole. So when we create it from the components, so for methane gas, it would actually be carbon solid plus 2H2 gas yields CH4 gas. So this would be the heats of reaction, or the equation for that. But the delta H comes out of this table. So how do we use this information once we have it? So there are a couple of guidelines for using delta H naught F. 1, in a decomposition reaction, delta H reaction is actually negative delta H, the heat of formation. So we could calculate that pretty simply from the table. So when we use delta H naught F, we're going to use it to calculate delta H of reaction. And so we're going to do that by calculating different states. So we can use the delta H naught F, and we're going to multiply it by stoichiometric values since they're per 1 mole. The other thing is, you'll notice on the table, if you look back, there isn't anything in its native state. So a native state is something like carbon solid, delta H naught F equals 0. O2 gas, delta H naught F equals 0. Chlorine gas, delta H naught F equals 0. So anything in its native state requires no energy to form it. Now, what does that actually mean? Let's think about, we want to make chocolate chip cookies. It requires a lot of energy to create it from its native states. So chocolate chip cookies are made from flour, eggs, all these components. So the delta H naught F requires a lot of energy. But the delta H naught F to get flour here in my home is nothing, because flour is already in its native state. Now you can make flour. That's not to say you can't. But in this case, we're talking about the ability or the amount of energy it takes to create anything per 1 mole. So let's talk about how we're going to use this information. So delta H reaction equals the sum of the delta H naught F for the products minus the sum of the delta H naught F for the reactants. So what does that mean exactly? So if we have an equation where 2A plus 3B yields 2 F's plus C. In this case, we know that delta H is mostly going to be calculated final minus initial. So we can utilize the delta H naught F's to basically calculate that. So our equation would be that 2 times the delta H naught F of F plus the delta H naught F of C minus 2 times the delta H naught F of A plus 3 times delta H naught F of B. So there are a couple of things that are pretty important. Make sure that you use parentheses here because we want to make sure that the negative sign doesn't get lost. And so it's products minus reactants, and you can read these values off the table. So I think it's worth, let's look at some examples. So in this case, the example says, calculate the standard enthalpy change for the combustion of 1 mole of C6H6 liquid, which is benzene, to CO2 and H2O. And we're going to use the table. And so I've made an excerpt of the table over here on the right side of the screen, just so that we didn't have to flip back and forth. So in this case, the delta H of reaction is going to be calculated. So we have delta H reaction equals the sum of the delta H naught F for the products minus the sum of the delta H naught F of the reactants. So let's start looking at that information. So it's going to be the products. So it's going to be 3 times delta H naught F of H2O plus 6 times delta H naught F of CO2 minus the delta H naught F of C6H6 plus 15 halves of the delta H naught F of O2. So now we can start to plug this information in. So the first thing we're going to do is we're going to look at the water. So we can see that here in our table. So it's going to be 3 times negative 285.8 plus 6 times CO2, which is negative 393.5. Now we're going to subtract 1 times the delta H naught F of benzene, which is 49, plus 15 halves the delta H naught F of oxygen. Well, that's not in the table. So let's think about this. Oxygen gas comes as O2 gas. So that's its standard state. So it's going to be 15 halves times 0. So this is going to go away. When we plug this into our calculator, what we're going to get out of this is going to be negative 3,267 kilojoules. And so delta H reaction, when we have standard enthalpy tables, is about plugging it in. So you'll always be provided a table or something similar. So let's look at another example. So in this case, the standard enthalpy change for the reaction, calcium carbonate decomposing into calcium oxide plus CO2 gas, is 178.1 kilojoules. Using the heats of formation table, I've provided some of the information. Calculate the heat of formation for calcium carbonate. So we want to know delta H naught F for calcium carbonate equals question mark. So this is a little different than it was in the previous example. So delta H reaction equals, in this case, 178.1 kilojoules. So we already know the heat of the reaction, so we're just solving for the heat of formation of calcium carbonate. So we know that delta H reaction is equal to the sum of the delta H naught F for the products minus delta H naught F of the reactants. So let's start plugging all that in. So we have 178.1 equals, in this case, we're going to look at our reaction and our information. So we have delta H naught F of calcium oxide, which is negative 635.5 kilojoules, plus negative 393.5 kilojoules, minus the delta H naught F of calcium carbonate. So then we want to solve for our delta H naught X, or delta H naught F of calcium carbonate. So the delta H naught F of calcium carbonate is going to equal negative 1207.1 kilojoules per mole. So it's really important to make sure that you keep track of your negative signs when you work this problem out. My guess is many of you ended up with a positive value if you attempted this. So make sure that you follow them when you either multiply or divide by negative numbers. So the heat of formation is another way that we can calculate the delta H of a reaction.